Okay, so let's talk about heaps. So our goal here is to come up with a better priority queue. And we're going to try and do that by a specific type of heap called a min heap. There's also the complement for this, the max heap. So min heaps are defined by two different properties. One of them is the shape property, and that's basically the shape of it has to be a complete binary tree. So if you remember, the idea of a complete binary tree is a binary tree that forms a perfect pyramid, or it's a pyramid where the bottom row is not completely filled in, but the tree builds from left to right, top to bottom. So that's one of the properties, the shape property. The other property is an order property. And for a min heap, the order property is about the less than operation, identifying a minimum element. So the property is that a parent's data value must be less than or equal to the data values in its children. Okay. By the way, less than is a transitive relationship, so that will be useful to us in a few minutes. So because it's a transitive relationship, what does this mean about the value in the root? We'll come back to that in a little bit, but go ahead and try and answer for yourself what you think this means about the value in the root of our tree. Okay, so before moving on, it's important to note that max heaps are also possible, and max heaps have a correspondingly different inequality. The parent's data must be greater than or equal to the data in its children. Okay, so let's look at some min heap examples. So here are 4 different styles of tree. Let's try and identify which of these are valid min heaps, and the ones that aren't, let's identify why they aren't a valid min heap. So this all comes back to those 2 different properties. So first of all, let's look at each in terms of the shape property. Going from left to right, looks like our first tree fits our shape property. Our second tree doesn't fit the shape property. So it's definitely not a min heap because it's not a complete binary tree. Next one over, yeah, that's good. And also that's good. Okay, so in terms of the shape, we're only throwing one of these out. Now let's look at the order property. So we'll look at each of the nodes here, and we'll identify whether the parent value is less than the values in its 2 children. So 1, that's less than 5 and 3. What about 5? That's less than 12. Yeah, we're good there. This leftmost tree is in fact a valid min heap. Let's look at the third one over. So again, starting at the top, 1 is less than 4 and less than 23. 4 is, there we have a problem. 4 is not less than 3, so the third tree over is not a min heap. The last one, all of our values are 12, so our inequality is less than or equal to, so this will pass our test, and it's also a valid min heap. Okay, so let's talk about the value that we can expect to find in the root. So we have a theorem here. In a non-empty min heap, the minimum value is in the root. So let's prove this, and we'll do a proof by contradiction. So we'll assume that we're wrong, that we have a non-empty heap, and it has a root node that is not the minimum value. And what that really means is the minimum element must be someplace else. Okay, so again, we're trying to demonstrate our theorem is true, that the minimum value must be in the root. By the way, that's going to be really convenient for us because we're trying to implement a priority queue and we want to find and extract the minimum value. So our assumption will be that the minimum value is not, in fact, in the root, and we'll try and prove that this leads to some sort of a contradiction. It will somehow contradict the definition of our min heap. So our assumption is that the minimum element is not in our root, it's somewhere else. So I'm going to draw out a fragment of a heap, and I'm only going to draw parts of it. So I'm going to draw the root node, and it's connected to a left and a right maybe, and I'm not going to worry about what's going on the left. And I'm just going to fill in some arbitrary values. And at some point, we get to the node that would have to contain the root, so the minimum value. So if we assume the minimum value isn't in the root, it has to be someplace else. I'm going to pick this arbitrary location, and I'm going to call this node A with a minimum value, so A min. I'm also going to think about the nodes along the path to that minimum value. So the things starting from the root all the way down until we get to that minimum value. I'm also going to give those nodes labels just so we can think about them in clear terms. So I'm going to call the root A0, and the next one down I'll call A1. So essentially I'm labeling these just with some variable name, A, and a subscript that represents their depth, distance away from the root. Okay, so this chain will continue, and the parent of our minimum value I'll call the nth node. Okay, so let's think about the property of our heap. So just by the definition of the heap, the parent's value, A0, should be less than or equal to A1. And A1 should be less than or equal to A2, and so on and so forth until we get to AN and A min. So again, that's just applying the heap property, the definition of the heap itself. And here's where we have our contradiction. So if this is a valid heap, if this property is met, then the minimum has to be greater than the value in the root. So this is our contradiction. Clearly the minimum can't be anywhere besides the root. So if the heap property is true, A0 must be the minimum value. So we've proven that the minimum value is in the root node of our min heap. Okay, great. So that's really handy because it will help us use the heap as a priority queue, particularly with our definition of a priority queue. So let's look at the insert operation, the extract operation, and our other two operations is empty and peek min. Okay, so how can we implement insert? So that's kind of an open question. We'll talk about all four of our operations and then we'll talk about how we can implement them. So extract the minimum. Well, we've just identified that the minimum is in the root. So somehow we just need to get rid of the root. So we'll leave that as an open question. We'll come back to that in a bit too. The good news is the other two operations are really easy. So peek min, that's easy. We just look at whatever value is in the root. We've got direct access to the root from our root reference variable. And is empty, we just have to check to see if the root refers to anything at all. So that's also really easy. Okay, now let's focus on insert, and then we'll come back and talk about extracting the minimum value as well. So in order to implement insert, we'll focus on the two properties of our heap. So if you remember, it had the shape property, and it also had the order property. So we'll even focus on them in that order. So the shape property, it's a complete binary tree. When we're doing an insert, the first thing we'll do is we'll insert a value in a way that ensures that we still have a complete binary tree. So as we saw with our tree building earlier, we'll basically pick the first available space on the bottommost row, or if the bottommost row is completely full, we'll start a new level down below that and use the leftmost position. So we'll add a node so that the shape is maintained. So that'll take care of our shape property. Then we'll deal with the order property. So if you remember, the order property is about ensuring that a parent's data is less than or equal to the data in its children. Okay, so if we've just added a new node and we already had a proper heap, then the only change is in that new node itself. So we can start by focusing on that new node and its parent. And if the value in the new node is less than the value in its parent, we can swap it as a first step to try and fix the failure in our order property. Okay, of course, then we've moved the problem, the new value, up one position, and now it may be out of order with respect to its new parent, so the original added node's grandparent. So we will have to repeat this process, and we may have to repeat it again and again. Okay, so let's be a little bit more concrete with this. So our process will be to somehow create a new node, add that new node to the first available position in the tree. So all about enforcing the shape property. And then after that, we'll enforce the order property. And we'll do that by starting at that new node. We'll consider it to be our current node. We'll check, as long as we are not at the root itself, as long as there's something above us, we'll compare the parent's value with this new node's, with the current node's value. And if the parent has a lower value, we'll go ahead and swap the two. And we'll update our current node to be the parent, effectively moving us up the tree one level. Okay, so we'll go through several inserts to get a sense of how this behaves. So first off, we'll insert 12. It'll be the first node in our heap, so it's there all by itself. There's no parent node, so our while loop won't do anything at all. Next, we'll insert 7. Take just a second at each of these and think about what needs to happen. So first we'll take care of the shape property. We will add 7 to the left as the left child of 12. So I'm going to go ahead and indicate that that's connected up. And then we have to go through, it's our current node, we compare it to its parent. We see that the 7 has a lower value than the parent, so we swap them, and we move up to the parent. And we're now at the root, there's nothing to compare to, so we're done. Okay, let's go ahead and insert another item, so we'll insert an 8. Again, take just a second and think about what you think it'll do. Okay, so first we'll take care of the shape property. So we will insert it to the right of the 7. We've now filled up the second level down. Next, we'll take care of the order property. We'll compare the 8 to its parent, the 7. 8 is not less than 7, so we won't do anything further. Another insert. This time we'll insert 9. Again, shape property first. We'll insert 9 as the first node on our third level. We'll go ahead and go through our while loop, comparing the 9 to its parent. 9 is less than 12, so we will swap them. And then we'll move up to the parent. We'll compare the 9 to the 7. 9 is not less than 7, so we're done. Okay, next, insert a 10. So again, shape property first. We'll insert the 10 to the right of the 9. 10 is our current node. We'll compare it to its parent. 10 isn't less than 9, so we'll leave it where it's at. Next, we'll insert a 5. Shape property first, we'll insert the 5 to the left of the 8. 5 is now our current node. We'll compare it to its parent. 5 is less than 8, so we'll do a swap. 5 is still our current node. We'll compare it to its parent. 5 is less than 7, so we'll do a swap. Move our current node up. Now we're at the root. Our while loop is done because there's nothing above the 5. Okay, so notice at each step of this, as we're done with our insert process, that our properties are met. We have the shape property, and we also have the order property. Okay, 2 more. Let's go ahead and insert a 2. So again, shape first. We'll insert the 2 on the last open position in the third level. Then we'll go through and take care of the order property. 2 is less than its parent 7, so we'll swap them and proceed up. 2 is less than 5, so we'll swap them and proceed up. And we're at the root, nothing else left to do. Okay, one more insert. This time we'll insert 11. So again, take a second, think about what's going to happen when it gets inserted. Okay, shape property first. 11 goes to the left of the 12. 11 is less than the 12, so we'll swap them. Proceed up. 11 isn't less than the 9, so we're now done. A quick review of our algorithm and identifying time complexities. So again, we're creating a node, adding the new node in the right place, and then we're going through this process to enforce the order property. So shape property, then order property. So we've seen things like creating a node before, so we'll argue that that's constant time. For the time being, I am going to claim that adding the new node in the right place to enforce the shape property is also constant time. we'll look at why I'm making that argument now, although there are different ways to implement this, and another way to implement it, we could justify that it's less than log time. So we'll come back to that, but again, for the time being, I'm going to focus on it being constant time. Then we've got to worry about this idea of the order property. So what's really important about this is that it may be going from the top of the tree to the bottom of the tree, or rather from the bottom of the tree to the top of the tree. And we've already identified that that's basically traversing the height of the tree. And the height of the tree is equal to log n. So we can argue that this process is also going to be proportional to log n. So it's a constant time operation, a loop that repeats log n time, and inside of the loop, the stuff that's being done is all constant time operations. Okay, just to tie it all together, we've got a constant time operation, something that for the time being, we're going to assume is a constant time operation, and a loop that runs constant time operations log n times. So our total would be log n plus some constants. We'll drop the constants, and we'll say that this is a big O of log n operation for insert. Okay, let's talk about the extract min process. So just like with the insert, we'll focus on maintaining the properties of the heap. So we'll focus on the shape property, that it's a complete binary tree. So in this case, we want to remove the root, or at least we want to remove the value from the root. So we'll take a kind of a shortcut. We'll actually swap the last item's value into the root and remove the last item. So we'll actually, in a sense, be removing from the bottom of the tree, but we'll maintain whatever data was in the bottom of the tree. We also still have to maintain the order property. So the order property is that any parent's data is less than or equal to the value in its children. So in this case, we're going to be changing what's at the root. So the only significant changes will occur at the root, and then we'll have to compare the root to its children and possibly make a swap. And then we possibly will have changed one of the children, and we'll have to continue the process. In ways, this is very similar to what we just saw with the insert process. So more concretely, the extract min will extract data from the root of the tree first, so that would be the minimum item that we want to return. Then we'll swap values from the last item to the first item and delete the last item, so that would be the bottom rightmost node in the tree. And then we'll go, so that was all about the shape property, by the way. And then we'll deal with the order property. So we'll start at that root node, and we'll continue until we hit a leaf. And at each node, we'll compare the value in the node to the minimum of its children's value. And if it's greater than the minimum child's value, we'll do a swap and proceed down the tree to that minimum child. When we're all done, whatever value we extracted in our very first step will return. Okay, so that's an overview of the process. So let's go through an example. So we'll pick up with the heap that we just had from inserts, and we'll start removing items. So let's start by extracting the minimum value. And again, remember that basically what we're going to do is extract the 2, and we'll remove the last node of the tree and essentially replace the root with the last node. Okay, so that's the first part of our process. The second part of our process is starting at the new root and comparing it to its minimum child. So it's got 2 children, the 9 and the 5. The minimum of the 2 is the 5. Remember, our end goal is to ensure that the minimum value overall ends up at the top of the tree. I want to pick the minimum child, which will ensure that the minimum value ends at the top of the tree. So I compare the 12 to the 2 children. 5 is the smallest, and it is smaller than 12, so I'll go ahead and swap those 2 values. So now I'm at this point. I compare it again to its minimum, the minimum of its two children. So it's got children that are 7 and 8. So 7 is the lower value, and again that's lower than 12. So I'll go ahead and perform a swap and proceed down the tree. And now I'm at a leaf node, so there's no more work to do. Okay, let's do a second extract min. So just like before, we will essentially be removing the root node and replacing it with the bottom rightmost node, which is again our 12. We'll repeat the process we just went through. We'll compare it to its minimum child, which is the 7. We will swap it. We'll proceed on down the tree. We'll compare it to its minimum child, the 8. We'll swap it, proceed on down the tree, and we're at a leaf. And once again, we're done. Okay, we're going to do this a few more times, so I'll go ahead and work through it kind of quickly here. So, by the way, we've got an interesting scenario here. Our maximum value is ending up at the leaf. So we swapped the, we extracted the root, we swapped in the last node in place of the root, we start at the new root, we find its minimum child, and we compare the two. The minimum child is less than the root value, we swap it, we move on down the tree. Okay. Repeat the process again. So take just a second, think about what's going to happen here. Maybe draw out a diagram and work through it yourself. Okay, so this next one, we're going to, again, essentially remove the head and swap in the final value, the bottom rightmost value. We'll again proceed on down the tree. We'll compare the 10 to the minimum of its two children, which is the 9. 9 is less than 10, so we'll swap the two values. Proceed on down the tree, compare the 10 to the minimum child. It only has one child. The child happens to be a value of 11, which is no less than 10, so we're done. Okay, repeat the process again. Remove our node at the root, extract it, move the last node into its place, compare the new root to its minimum child, the 10. 10 is less than 11. Do our swap. Proceed on down the tree. We're at a leaf node, nothing more to do. Okay, one more time. Remove the 10. Swap the last node into its place. Compare the new root to its children to find the minimum value, to swap the minimum child into its place. So the minimum child has a value of 11, which is less than 12. We'll swap it into place. Proceed on down the tree. We're at a leaf. There's nothing more to do. Repeat the process one more time. Remove the 11. Swap the 12 into its place. It's now a leaf node. There's nothing more to do. One more time. Remove the 12. And we're done. Something that's interesting to note here is that we extracted all of the values and we got all of the values in purely ascending order. Just like before, let's do a quick overview and try and identify the complexity of this. So we've got the extract process, and we can argue that that's probably constant time. We're just retrieving data from the root node, and we've got direct access to the root node through some sort of a root variable, kind of comparable to the head variable in our linked lists. We've got the move and swap from the last node. If we've got quick access to the last node, we could argue that that's also constant time. So again, I'm going to claim this. We'll come back to this in a bit. Then we've got our process of enforcing the order property, which will go down the tree. And just like before, we know that this while loop is going from the top of the tree to the bottom of the tree in this case, and we know that that's the height of the tree, and the height of the tree is equal to the log of n. So our total, then we have to return the extracted value. Just like before, we can kind of summarize this and come up with a total. So we've got several constant time operations, a log n operation, and a constant time operation. So the loop runs log n times, but it's doing constant time operations in the loop, so it's 1 times log n. Anyway, our total ends up being log n.